So welcome all for coming. My name is Djorgovski. I'm a professor at Caltech, and today I'd like to tell you about some of the work that I do along with many other colleagues. So as I noted in the introductory sentence on the note card, cosmology is the part of astronomy and physics that deals with the universe as a whole. And by that we mean two things. One was to first figure out how the universe evolves geometrically and dynamically, the expansion of the universe due to the dark energy and dark matter and things like that, as well as the physics in the very early universe. The other half of cosmology, so to speak, it is to understand how the structures that we see in the universe at large scales, that will be mostly galaxies, but also large-scale structures of clusters of galaxies and filaments and voids and things like that. How did they form and how did they evolve? So that's what I will be talking about today. And there's been a lot of progress in this field over the last couple of decades, but especially over the last couple of years, thanks to James Webb Space Telescope. And I will show you some of those results. So during the talk, please mute your mic, use the local chat to exchange your thoughts. At the end, we'll do the Q&A. And so that I'm not confused as to what are the questions, please indicate them like this in the local chat. And so then I'll just go in order. All right, so let's begin then. First, I will describe some background that you will need to understand for the rest of the talk about the expansion of the space. What is the cosmological redshift? That's our measure of distance. Where does it come from? And then I'll start talking first about where did the fluctuations from which all structures grow later on originate in the very early universe. And as you'll see, dark matter also plays an important role in the origin of galaxies. Then there'll be some stages in the evolution of the universe. First, when original hot plasma consisting of electrons and protons and other particles recombines to make neutral atoms, and that's where the so-called cosmic microwave background is released. Then how the first stars form, and then they reionize the cosmic gas again into the transparent plasma, and galaxy evolution commences. So let's start with that. First, about the expansion of space, which a lot of people do not fully understand. You should first realize that there are really two kinds of spatial coordinates. There are coordinates that you know and love, so-called proper coordinates, and that things are fixed in those. You, rulers, planet Earth, solar system, Milky Way galaxy. And those coordinates do not expand. Then there are so-called co-moving coordinates, which do expand. The space does expand, and so you have to have two kinds of coordinates because of the expansion relative to what. So there are things that do expand with space and things that don't. Things that are bound by gravity or some other force, gravity in case of stars and planetary systems and galaxies, or in terms of atomic forces, rocks, planet Earth, people, they do not expand. They do not partake in the expansion. But things that are not bound together by one of those other forces are carried apart by the expansion of space. And that's how we can tell that space is actually expanded. This is now 100 years old, the original discovery by Hubble and others, that this is the case. And the way this works out is the expansion is uniform everywhere in space. So if something is near you, it'll be moving away from you. say, a galaxy relatively nearby. And then galaxies further out will be moving away faster because they all have to be moving apart from each other at the same rate. Because of that, the apparent velocity of galaxies moving away from us would be proportional to the distance. And that's what makes it possible to actually determine the expansion. We can measure the velocities by using spectra, and you're all probably familiar with the Doppler shift for sound, where ambulance approaches, the pitch is high, it goes away from you, the pitch is lower. And so the same thing applies to any waves, including electromagnetic waves, such as light. And since the atoms emit radiation in a very well-defined, fixed manner, we can look at the spectra of stars from distant galaxies, compare them what they would be like if they were not moving away from us, and from their displacement, we can figure out how fast they're moving. Now, something to point out. This is slightly different from the Doppler shift that we're used to in classical physics, where something is accelerated to some speed, and then you measure that speed through Doppler shift. Galaxies are simply carried away by the expanding space. So that velocity is not the same kind of velocity that you do in Newtonian mechanics. But it has to be consistent with classical physics, and so it is exactly like the Doppler shift. Another important part of this is, well, the wavelengths are systematically stretched. And so photons that leave from some distant galaxy, that may be from ultraviolet, then gradually get stretched by the expansion of space as they propagate through the universe coming to us. And they may arrive as visible light or infrared light photons. So this is why we call it redshift, because the wavelengths go from bluer to red as the photons travel. And this is a well-understood relation, and when we talk about the redshift, which astronomers commonly denote with a lowercase z, redshift of 10 means that the universe was 11 times smaller at the time, and the wavelengths of photons that come from there are now 11 times larger. Redshift of 1 means that the universe was half the current size, and photons got stretched by a factor of 2. So it's 1 plus redshift that gives you the stretch factor. So this is the basic observable quantity, and then once we have right cosmological model, we can convert this observed recession velocity to actual distance and the time that has elapsed since the photons have started. That's what makes cosmology possible. So another implied thing here is that, in some sense, the universe has its own built-in time travel machine. The further away in space we look, the deeper in the past we look, because it took longer for the light from more distant sources to come to us. So we see them as they were when the light left. They probably evolved since then. But if you know something about theory of relativity, we call that the surface of the past light cone. So we're only looking at one three-dimensional slice of the four-dimensional space-time. But because we make a reasonably good assumption that the universe is same everywhere and in all directions, that's called homogeneity and isotropy, whatever we do observe is presumably statistically the same as in other parts that at the same time that we do not directly see. So this is again what makes cosmology possible. By being able to look far away, we can look deeper in the past. And since everything in the universe evolves, including galaxies, clusters, stars, then if you want to understand it, you want to measure how it evolves, you have to look ever further and further distant examples thereof. So that sets the stage of how we actually measure and know these things. Here is a cartoon version of the overall history of the universe. It starts classically at least, with the Big Bang. There is no space and there is no time. Before then, the space expands, matter and energy expand at the same time. Big Bang wasn't like an explosion in some point and then stuff flies away from there. Now the space was also in that point, which takes some time getting used to, but that's how it is. Einstein said that's the case, so therefore it must be right. Okay, so that happens very, very early on, and we do not yet have the physics that will tell us exactly what happened then. We would need to have quantum theory of gravity and all kinds of other stuff. But the very earliest moments of the universe are beyond from we actually know and measure. With one important possible exception, which is so-called cosmic inflation. We now think that when the universe was approximately 10 to the minus 32nd power seconds old, it underwent a brief period of exponential expansion due to some as yet unknown physics, but properties of the expansion we can explain. And we cannot probe those directly, but it makes predictions of some things that are extremely difficult to understand otherwise. In fact, it's such a natural explanation based on everything else that we know that most physicists believe that something like that must have happened in the early universe. And there are some ways in which we can try to constrain that. But be that as it may, it expanded. The important thing is that not only does the space expand, but carries things with it. So any fluctuations that may have happened in the early matter and energy due to the quantum fluctuations, which are inevitable if quantum physics applies, they also get blown up in size. In fact, all of the big structures we see today, galaxies, clusters, superclusters, probably come from subatomic, subparticle scales that were then inflated to the sizes we see through this process. Anyway, universe is then filled with very hot plasma, quarks and gluons and things that were there before them and so on. Eventually particles that we know like protons and neutrons and electrons are formed. And it's all hot plasma embedded in expanding space with radiation that also expands. And when the temperature drops down to about 3,000 degrees Kelvin, it's no longer hot enough to maintain this fully ionized gas. And so protons and electrons and other nuclei recombine to form neutral atoms, neutral gas. This is what we call the cosmic recombination that happens when the universe was 380,000 years old. And we know that number from studies of cosmic microwave background. Before then, the universe was opaque to any radiation, just like stellar surfaces now. If you look at the surface of the sun safely, of course, you see a ball of incandescent gas, and you can't see in it because plasma like that is always opaque. Once it's no longer plasma, but just a neutral gas, you can see through. And so in some sense, the universe becomes transparent past this point of recombination, except that it's filled with gas, mostly hydrogen, helium, trace amounts of other elements, and hydrogen can absorb ultraviolet light very well. So it's basically, the universe is transparent at all wavelengths longbird of, say, roughly 100 nanometers, including radio waves, which is why we can see cosmic microwave background. There are no sources of light at this time. It's just a slowly cooling plasma or gas at that point. Dark matter, however, plays an important role in this period, and it actually originates formation of structures. And regular gas, mostly hydrogen, helium, then flows into dark halos, potential wells defined by the dark matter. Gets compressed. When it gets compressed enough, it makes stars. This is how stars are made even today, from gas that reaches high enough densities to ignite stars. This happens when the universe is roughly 100 million years old, give or take factor of 2. And then first galaxies form, and the light from hot young stars in those first galaxies reionizes the gas again. And when the universe is about a billion years old, it again becomes fully ionized. So it starts as a fully ionized plasma, then becomes neutral gas, then gets to be reionized by the energy input from stars. In that time interval, from the formation of first stars until full reionization, we think of it as cosmic renaissance, was the period when there are no sources of light we call cosmic dark ages. Well, that is when the first galaxies form, and that is now the territory that is being probed by the James Webb Space Telescope. And then there is no sharp transition of, well, now the galaxies are made, now they start evolution. Evolution really begins from the clouds of dark matter and carries on. But then from roughly the age of a billion years until today, about 13.8 billion years after the Big Bang, is all of the regular galaxy evolution that we observe. So what is the challenge here? We see on the cosmic microwave background sky, and that's this picture shown in the upper left. This is actual data from measurements by satellites like COBE and Planck and WMAP. We see that there are very slight fluctuations. Cosmic microwave background, the radiation that fills the universe from the original Big Bang, is extremely uniform. And if you turn the contrast knob by a factor of a million, you see that there are these non-uniformities encoded here with colors, with hotter colors being hotter temperature, cooler colors being cooler temperature, by roughly parts in a million. So those are the fluctuations from which the large-scale structures and then galaxies within them will form. Today in the universe, we see large-scale structures, clusters, filaments, voids between them, and the density contrast today, say, of these large-scale structures and the relative to the average density of the universe is roughly a factor of 100. So you go from part in a million to factor of 100. But when you then look to smaller scales of galaxies, the average density within visible parts of galaxies is a million times higher than the average density of the universe. So how do you go from such a low contrast to such high contrast? That's basically what formation of structures in galaxies is all about. And we actually understand how that happens. But let's start at the beginning. I mentioned earlier that everything starts from quantum fluctuations in the early universe. Back before quantum physics, vacuum was vacuum. There was nothing there. But in quantum physics, we know that vacuum is actually quite alive. It's filled with what we call virtual pairs of particles and antiparticles that come into existence very briefly and annihilate, and that's governed by the so-called uncertainty principle. This is actually a measure effect, and we know that this really happens. Those particles cannot be observed directly while they exist or come out of this boiling cosmic vacuum, but their effects can be measured, and in fact people got Nobel Prizes for this. But remember, there is inflationary period, and then things that are on subatomic scales of 10 to the minus 14 centimeters, if you will, or something like that, can get blown up to scales of 10 to the 28 centimeters. And that is essentially the fluctuations that we see in the cosmic microwave background. They're the descendant of microscopic quantum fluctuations in the early universe. Now comes the interesting portion, that dark matter and regular matter evolve a little differently. Dark matter is following only gravity, and general recipe for structure formation in the universe is it's the self-gravity. Denser parts will be attracting matter from their surroundings, so more matter will be falling towards the denser spots. It's just like in real life, the rich get richer, and so that's how fluctuations grow under their own self-gravity. There is nothing to stop them from doing so in the dark matter. So they could, in principle, all make black holes, but some of them do probably, but not all of it. Regular matter, however, is first held against falling into any of these potential wells by the balance between radiation and regular matter. Photons are streaming around with speed of light. Just essentially they have their own gravity. That's the famous E equals mc squared. Energy and matter exert gravity on each other. And until the universe becomes neutral, regular matter cannot really participate in the formation of these structures. Dark matter can. And then you have these pre-made dark matter halos, and regular matter falls into them. And that's when it can start making stars. So then those stars will then reorganize the universe and so on. Well, what I'm showing you here in the lower right is actually simulation, not real observations. But that's roughly how it happens. Okay, so again, the original energy fluctuations, which then become density fluctuations, again because E equals mc squared, originate from quantum processes in the early universe, which we do not understand in detail. But if quantum physics applies, then this would happen, whatever the actual origin of fluctuations is. There's some particles that no longer exist. And then those are inflated, and the important thing that we can try to measure is how many of what size there are. So we call that the mass power spectrum, and it's shown as the diagram in the lower right. And what's shown there is essentially logarithm of how many there are, or which size, versus logarithm of inverse size. The k in that x-axis is 1 over the size. You can think of it that way. So there are a lot of small ones and not very many big ones. And the theory gives us the exact shape for this relationship, which amazingly enough is borne out by the observations of the cosmic microwave background and then other observations afterwards. So we have some confidence that this is actually, that we understand some of it. We don't understand all of the physics, but we understand what happens once such a process can start. Okay, so this is a little tricky. This is why dark matter is important in this. Take good notes, there's going to be a quiz at the end. Just kidding. So at first, the universe is dominated gravitationally by radiation, photons. Again, E equals mc squared. However, what happens is that as the universe expands, the density of the regular matter goes as 1 over cube of the expansion factor. It's just volume dilution. For the photons, there is also that 1 over cube of the expansion factor, again dilution, same number of photons in the bigger volume, less density. But also, the photons are stretched by the expansion. So they actually, their energy density goes 1 over the 4th power of scale factor. So originally, radiation dominates by about a factor of 1 billion. But then as the universe expands, it really becomes less important because the density gets to be diluted more than density of regular matter. And when the universe is about 50,000 years old, density of the regular matter, or dark matter I should say, becomes the driving factor of the expansion of the universe, as well as any structure formation. And this is when original quantum fluctuations start growing. the material falls into the potential wells created by dark matter. Meanwhile, the regular matter cannot grow. It just goes by the radiation, where the photons are. So by the time the recombination happens, about 330,000 years later, there are already well-formed dark halos, dark matter halos. At that point, the regular matter is now free from radiation, can start falling into them, and eventually they grow in concert with each other. But it begins with dark matter. This is one of the reasons why we think dark matter really should exist. I mean, we have direct evidence that it exists, but if it wasn't for the dark matter, there won't be structures that we see in the universe today. The universe would be more of a like uniform, slightly fluctuating mush. So that's an important role that dark matter plays. Now we can simulate this in a computer, in fact, extremely well. And as far as the dark matter, which dominates the density and therefore everything else, is concerned, it's at that point just Newtonian gravity, except there are gazillions of particles. You can't do that analytically. And the art of simulating structure growth of dark matter in an expanding universe is now extremely well developed. And these are snapshots of some simulations. The number in the corner, Z, redshift, is what will be the actual redshift when the universe looks like that. And you can see that density contrast keeps growing. Material falls towards the denser spots, therefore evacuating space around them. This is the origin of cosmic voids. And smaller things merge into bigger things. There is constant merging of structures into ever bigger ones, so we call it hierarchical structure formation. In the meantime, also gas follows where the dark matter does, and then gas will be turned into stars, and that's what we can actually see. So there are really two parts to galaxy formation and evolution. One is the assembly of the mass, which we can simulate extremely well, and the other one is turning gas into stars, which we can also simulate, but not quite as well, because it's a vastly more messy and complex process, but with modern simulations, we can pretty much do it. So people run well model universes in a computer like that, and then they predict what they should look like, compare it with the actual observations, adjust parameters as needed. And long story short, we now think we really understand how this process works once it starts. And observations are in excellent agreement with these models. There is another subtle part to this, which is how much density contrast can you achieve just from gravity alone versus needing something else. So say you have a blob in an early universe, and it's got density contrast of 1. When it falls upon itself under its own cell gravity, the equilibrium is reached when it's 1/2 of its initial size. That's from so-called virial theory. So that leads you to a density contrast of 2 cubed, which is 8, so roughly 10. And if it was just gravitational formation, that's the density contrast that you can achieve. However, while that's going on, the universe around it keeps expanding. So the density contrast relative to the surrounding universe becomes larger and roughly becomes factor of 200 by the time it's all settled, which is exactly the density contrast that we see for large-scale structures in the universe today. So we understood where that comes from. It is collapse under cell gravity plus the expansion of the universe around the regions that collapse. Great. But remember, then there is an extra factor of approximately 10,000 or 1,000 from large-scale structures to galaxies. How do we do that? Well, that means that galaxies, the visible parts of galaxies, have to collapse by another factor of 10 or thereabouts. The only way in which they can do that in a self-gravitating system is if they keep losing energy. Because it's the kinetic energy, thermal energy that holds stuff against its self-gravity. And so if they lose energy, say through radiation, shocks and stuff like that, then they can collapse by factors that are larger than a factor of 2. They can easily get another factor of 10. So that is the difference between the galaxies and large-scale structures, that for galaxies you have this extra dissipation of energy that makes them denser by another factor of 1,000 or 10,000 relative to the large-scale structure in dark halos in which they live. And that really kind of explains everything that we really see. If it wasn't for this dissipation of regular matter in young galaxies, galaxies would be just kind of smeared along the large-scale structure. It won't be like well-defined individual shiny objects in the universe. And we can simulate that very well. Really superb numerical simulations on supercomputers these days. This is a picture of one of them. It shows what dark matter does, what gas does. Then some stars can explode, roll of radiation, shocks, and whatnot. It gets to be pretty messy, which is why you need supercomputers to do something like this. All right, so I mentioned that gas pours into the first protogalactic halos and eventually gets to be dense enough to form stars. I mean, this is how stars are formed, even Milky Way today. You have giant molecular clouds of gas. They collapse in their own self-gravity. They dissipate a lot of energy through infrared radiation. And eventually the cores of those clouds become dense enough to ignite thermonuclear reactions. They become stars. Well, the same thing happens early on. But there is one important difference. Energy dissipation of protostellar clouds happens through whatever radiative mechanisms are available to them. If you have a variety of chemical elements, carbon and oxygen and so on and so forth, you have a whole lot of different molecular energy transitions that can be used to cool protostellar clouds. But early on you don't. Early on you only have hydrogen. Helium too, but helium is hard to ionize. So first protostars, I should say, can cool only through radiation from molecular hydrogen, and that's a far more restrictive way than stars have today. Because of that, they get to grow bigger. And in fact, we believe now that the very first generation of stars, that we call population 3, will be very massive. Today, the most massive stars that are made in the local universe may be 100 solar masses, maybe even less. But some of these first stars could be many hundreds, many thousands of solar masses. And that also means they'll be extremely luminous, and they'll be also extremely hot. Because of that, there'll be really brilliant sources of ultraviolet radiation. And that is the radiation that turns the universe again into the ionized gas. But also massive stars do explode very quickly when they run through the thermonuclear fusion possibilities. And so those first stars, population 3 stars, will explode as supernovae, just like massive stars do today. They will release all of the newly made heavier chemical elements, starts just with hydrogen and helium, builds up to things like carbon and oxygen, magnesium, all the way up to iron and so on. And then more stars are made from that chemically enriched gas, and that process continues to the present day. So that, but they also leave remnants. When massive stars explode as supernovae, they leave a very dense remnant. If they're up to maybe 8 or 10 solar masses originally, the core of the star that explodes becomes a so-called neutron star. It's essentially a gigantic ball of neutrons, about some tens of kilometers in diameter, high density, and if you have high magnetic field, that's what makes pulsars. If it's more massive than that, it will make a black hole, stellar mass black hole. In fact, that's the only process we now know that we know can lead to formation of black holes. And all of the black holes we've seen until 2015 were remnants of massive stars that exploded, and they have something else near them, and that's how we know there is a black hole there, because of the gravitational effects. But now we also have gravitational waves, and they can detect mergers of binary black holes. So you have two really massive stars, each of which exploded, left the black hole as a remnant. Eventually they spiral in, merge together, and that process releases a burst of gravitational waves, which gravitational interferometers like LIGO or Virgo can detect, and they do. And now there are many tens of those that have, well, hundreds actually, that have been detected. And so we have this new way of looking at the sky in gravitational radiation, not just electromagnetic radiation. Okay, so this is how you begin with visible parts of galaxies. The dark ages, cosmic dark ages, and there are now new sources of light, and they cook up new chemical elements and make stellar black holes and reionize the gas. And so that's what we call the cosmic reionization. The halos grow, galaxies grow. Here again, some snapshots from simulations in the middle, and eventually those are the young galaxies, which then keep merging, making bigger galaxies, but you have very complex interplay of gravity and radiation and stars and dark matter and so on. So here is now a cartoon history of what happens after the recombination, when the microwave background radiation is released at the age of 380,000 years after the Big Bang. Then around 200 million years afterwards, first stars and galaxies form. And each of those blows a bubble of ionized gas around it. This radiation propagates slowly through the intergalactic hydrogen, turns it again into ionized gas. And when those bubbles start overlapping, percolates if you will, then all of the universe becomes transparent to ultraviolet radiation again. And that is what we call the end of reionization. And then from then on, we can easily see, well, not easily, but we can see galaxies in ultraviolet light, young hot star photospheres in them. So that's the region in which James Webb Space Telescope is now making huge advances. There is another trick that we use in order to find very distant galaxies. If they're far away, they're going to be very, very faint. And so anything you can do to make them more detectable is good. The obvious thing is big telescope, and another obvious thing is way outside Earth's atmosphere, so you don't have absorption and blurring by the Earth's atmosphere. But we also use so-called gravitational lensing, which is one of the basic predictions of general theory of relativity. That gravity bends paths of light rays. This is how general relativity was experimentally demonstrated in the first place by Eddington's expedition to see displacement of stars in solar eclipse. So if you have something really massive, say a big cluster of galaxies, and they tend to weigh around 10 to the 15 solar masses worth of stuff, about 5/6 of that is dark matter, then they will bend bend light rays of galaxies behind them. And they will both magnify those background galaxies and also distort their images, typically stretch them along the circles that are centered on the center of the mass. So we've seen that. I mean, first lensing was found observationally in 1979, and then clusters of galaxies have been used to this effect, both from the ground and Hubble Space Telescope very effectively to find most distant galaxies we knew before. And now exact same thing, same trick is being used with James Webb Space Telescope. It's not enough to have 6.5 meter diameter telescope in Lagrange point. you want to add this gravitational 4 optics to it to see even further, things that even James Webb wouldn't be able to see. So here it is. It's the artist's conception, obviously. It consists of these hexagonal segments. The technology was first proven on the ground with the Keck telescopes in Hawaii. Excuse me. And those mirror segments are literally gold-plated, and not because NASA likes to spend money, which they do, but because gold provides the best reflectance for the infrared radiation. And James Webb was optimized to work in infrared for a couple of different reasons. You can look through the dust clouds in infrared, see obscure universe, but also remember wavelengths of light get red-shifted, so light that left young stars far away as ultraviolet is now in infrared, and that's why. So here is the very first picture taken with James Webb Space Telescope, and they're looking at the foreground cluster of galaxies that we already knew had lens galaxies more distant ones behind it. And so those are these little arclets that are kind of seen concentric around the big galaxies in the cluster. And it's a beautiful picture and demonstrated the telescope works exactly as was expected, in fact, even better. So let me show you some more of those images. They also done deep images of what we call blank fields without one of those big lensing clusters of galaxies in front, because those are not unbiased chosen things. They'll let us see a little deeper, but you'd like to see also what average universe looks like far away. And so several different surveys have been done by different teams. One was Jade's from James Webb something, and they looked at the fields where Hubble also taken deep images with a lot of other data taken from the ground and so on, and they can see deeper. And so every single bright pixel in this image is at least one or more galaxies. There are a lot of galaxies out there in space. In fact, something like 1 trillion or so down to the limits we can see within the observable universe. This is a little zoom in on the same picture, and again, every single pixel that's not black has at least one galaxy in it. It's amazingly rich data set, and people are still analyzing those images. So how do we know which of these faint little galaxies are where? Most of them are way too faint to obtain spectra and measure directly how far they are. So we use this trick. The spectrum of galaxy dominated by young stars is very blue because young luminous stars are very hot and very blue, actually dominating ultraviolet. But if you look at that galaxy from the outside, it's surrounded by still neutral hydrogen. There's also a lot of neutral hydrogen in the galaxy itself, just like the Milky Way. And that hydrogen is going to absorb very effectively any light at wavelengths shorter than approximately 100 nanometers in its rest frame. And so what you see then is the spectrum of galaxies very blue, then suddenly it cuts off at the wavelength that corresponds to that absorption edge of neutral hydrogen. And hydrogen is very abundant, and this is kind of guaranteed to happen. So now if you take pictures in at least 3 filters, at least one of which is bluer to that cutoff, and the other to the red, you'll see a galaxy that is there in redder filters, and then suddenly disappears completely in the blue filter. And that's indicative of the presence of such cutoff in the spectrum, and from that position of the cutoff, we can find out how far it is. That works amazingly well. And this was done with Hubble and also from the ground as well. So here are some of the examples of this, the so-called dropout selection. Each row here is a different galaxy. Each column is a different filter and go from short to the long. And you can see for all of these, on the right, see a galaxy or even pair of galaxies. And then as you go sufficiently to the left, they get a lot dimmer or just disappear. And that's exactly the signature you expect from what I described to you. So this is how we can then, by modeling careful photometry of these objects, we can infer what is their redshift just from these multicolor filter images. But you'd really like to also get real spectra, and for some of them we do. So here are some more examples using false color. These are 5 pairs of images. The one on the left would be short wavelength, the one on the right would be longer wavelength, and you can see that again, on shorter wavelengths, galaxies are a lot dimmer or just disappear altogether. And then you can model photometry and find out that typically a redshift of the order of 10, give or take a couple of those. So the universe was about 10% of its present size at the time, and that means the universe was only a few 100 million years old at the time. Now, ideally, you'd also like to get real spectra, meaning disperse the light, look for emission lines or absorption lines of well-understood transitions of atoms and ions, and that kind of confirms that this multi-filter approach works. Fortunately, there is a powerful spectrograph from James Webb as well, and they've done that. Here is an example of one of these fields, and lo and behold, the first method works fine. It's just much cheaper observationally. This is probably the best observed one. It is the most distant galaxy that was known before James Webb Space Telescope. It was detected by Hubble. Early spectrum was from the Keck telescope, nothing like this one. This is like spectacularly high quality spectrum for something that distant. It's a redshift of 11, meaning the universe was 8% of its present age. And you can see there's a whole lot of emission lines that we can identify that nails down its distance and tells us about physics, what goes on in there. So that's how James Webb is now probing this region of early galaxy formation, universe from ages of a couple 100 million years to about 1 billion years after the Big Bang. But it's not just stars. Black holes also form. And in fact, we've seen quasars, which are luminous objects powered by accretion onto big black holes. And we know that they co-evolve with their stellar galaxy hosts. But it's really hard to make very massive black holes so quickly. Whatever the source of the black hole is, usually could be some massive stars, living black holes, they merge, get bigger, and so on. But it's also possible that the material can directly collapse into a black hole without going through stars. In any case, you need to make black holes that are millions to hundreds, maybe tens of millions of solar masses in the span of a few 100 million years, which is extremely hard to do. You have to kind of turn all the knobs in one direction and then some. And so here is what's probably the best case that we have so far, found as a combination of images from the James Webb and X-ray images from the Chandra satellite, which NASA in their infinite wisdom is about to turn off. And when you see an X-ray source that can be detected that far away, we know how far away is from the Webb observations, that kind of X-ray source can only be powered by really massive black hole accreting material, producing X-ray luminosities of the order of 10 to the 11 solar luminosities in X-rays alone. Nothing else can do that. So we now see direct evidence for the very first supermassive black holes, the birth of quasars, if you will, in addition to the birth of galaxies. Actually, this work that I'm showing you was led by a friend of mine, Priya Natarajan, who just got to be chosen as one of the 100 most influential people by the Time magazine. And I can assure you, nobody was more surprised than her. All right, so to recap what James Webb has done for us. So it's now finding galaxies when the universe was only like 300 to 500 million years old, which is like vast improvement from what we can do before. They were more luminous than people expected, and at first you saw reports in popular press that this is a real puzzle and how can that be and so on. It turns out there is no real puzzle. Just the initial analysis was a little too hasty, and we can now understand why they have the brightness they do, and they're not as massive as people thought they were, because it depends on some assumptions about the distribution of stellar masses, the history of star formation. So if they're dominated by massive stars, which is what we expect, remember the story about population 3 stars, and if star formation occurs in bursts, which is a natural thing to happen as opposed to continuous growth, then this is exactly what you should see. And we're starting to see also simultaneous birth of first quasars. And over the last several years, this has completely transformed our knowledge about galaxy and black hole formation. Well, not transformed, but affirmed some of our expectations and let us improve the models because it actually gave us some empirical evidence of how things work. All right, so to close, first things to remember that all galaxies and larger scale structures originate from these tiny density fluctuations in the early universe. This origin is still not well known, but it's consistent with what we know about quantum physics. These fluctuations grow to be bigger through their self-gravity, absorbing more and more material. And then first the dark matter does it, and then regular matter does it. After the universe becomes neutral, electrically neutral, at the age of 380,000 years, then the regular matter follows that. And then first stars eventually form. In the first proto-galaxies, the universe is 100, 200 million years old. That ends these cosmic dark ages, but there are no sources of light. Then those young stars fully reionize the universe again, become made transparent to the ultraviolet radiation, so we can actually study some of those first galaxies. And that frontier is now when the universe is at the ages of 300 to 500 million years old. Okay, so with that, I'll stop, and now I can actually take a look at your questions.
I'm going to post, George, I'll post the questions, beginning with the orange planar first.
I can scroll back and take a look. All right. So if space-time is being stretched, does the distance between things increase from our perspective? Yes. All points in the expanding space move apart at the same rate per unit distance. And so if two galaxies are a certain distance apart, and they're moving at some rate, but galaxies twice as far will be twice that rate, and so on. Let's see, what is the composition and percentage of gases? Well, at first, there is only hydrogen and helium, and roughly 3 to 1 in mass of hydrogen relative to helium. It's just tiny, tiny amounts of maybe lithium and beryllium. But everything else is cooked up in stars later on. Okay, Dali's question. No, there's a question in lowercase. Use caps, please. Is dark matter not a form of dark energy? Sometimes I hear these terms interchangeable. No, they're very, very different. Dark matter is matter like we know, except it's made from some particles that we don't know yet. From a variety of its behavior and properties, we know it's made out of particles. It's just they're not particles that we have produced in accelerators yet. And once we'll find it out, there will be progress in particle physics. Dark energy is totally different beast. It's really a property of space, of space-time. Unlike any other form of energy so far, well, first of all, it's not conserved. Its density of that energy per cubic centimeter, if you will, is constant. As the space expands, there are more cubic centimeters, so there's more energy. And it behaves like nothing else ever. So we do not know what its origin is. You can think of it, it could be just another constant of nature. Energy density is constant. You know, gravity has Newton's gravitational constant, is what it is, and so this cosmological constant could be whatever it is. So it's not for the lack of trying. There are thousands, literally thousands of papers, people trying to understand where it comes from. Even I wrote one. But we simply don't know. And I think understanding dark energy will require some serious paradigm shift, similar to maybe in scope like general relativity was. Or maybe it'll just require knowing quantum gravity and something like that. Dark matter will expand our knowledge of particle physics, but not be as fundamentally difficult to understand as dark energy. Let's see. Is the dissipation of energy the galactic scale expressed as a radiation of energy which allows us to see them? Yes, in part, that's true. I mean, I kind of implied that this is really electromagnetic energy, which is usually how regular matter can get to dissipate energy through electromagnetic radiation, and that's what we can observe at some wavelength or another. Okay. Simple question. The light you see in other galaxies, is that from collisions of expression a long time ago, or current suns going in the other galaxies? No, those, by and large, those are stars in those galaxies that we see at the time the light left. So, in some sense, that's equivalent to stars in our galaxy.
George, I kind of do have a question. After a star has broken up and left a black hole, why is it magnetically strong and it draws matter into that black hole? And then where does that matter go?
Well, it has nothing to do with magnetism, it's just gravity. And it goes into the black hole. Black holes grow by accreting additional material. That's their nature.
So what I was aiming at, I mean, it's not like we're going into a different plane of existence and all that. It's just that if matter gets absorbed into the black hole, it just breaks apart and that's it? It disappears?
Well, it's inside black hole in some form or another, but we cannot observe it. Probably regular matter all gets torn apart to elementary particles during that process.
Well, then is there any concern? You know, I've heard people say that, oh my God, the universe is going to get swallowed up by a black hole, and that's, you know, what's going to happen. It's going to end our existence. Is there anything like that science fiction taking place, or no?
Nope. As far as we can tell, the universe will expand forever, at least for a long, long time. Some small fraction of stuff ends up in black holes. Roughly speaking, over the history of the universe, maybe 0.1% of all matter ended up in black holes, and it's getting harder because things are flying apart?
Well, I was thinking that the simple question that I asked in the beginning was that as galaxies are forming and kind of attaching or morphing, I don't know how when you're going to integrating other smaller galaxies, doesn't it create a kind of energy? That's why I asked about what was the composition of gas. Is that kind of creating like a combustible thing, that a catalyst, for instance, when this happens, and is it creating a type of energy which influences galaxy formation?
No, nothing like that. Stuff falls in black holes before it falls, and it can get very hot and shine a lot of light, which is essentially how quasars work. We have a question. Very good question. What scale does the expansion manifest? Galaxies move apart, but locally we do not express that. It manifests itself at all scales, but it's too small to detect at relatively small scales, the scales less than megaparsecs apart. But even at scales of several megaparsecs, galaxies also get their own, what we call peculiar velocities, due to the acceleration by nearby masses. For example, Andromeda Galaxy and Milky Way attract each other gravitationally, and they're moving towards each other, even though they're sitting in this expanding substrate of co-moving coordinates. So you really start to see expansion, cosmological expansion, dominate over these local velocities at separations greater than several megaparsecs. I think I got them all. And it's 12 noon, so the time is up. Thank you all for coming, and thank you all for listening.